Anciently, revolution has been linked to expanding and rising up in size. From big cities and huge buildings, enormous factories and gigantic vehicles, even to large populations and communities. However, what is happening now is the exact opposite. For the last decades, the world has witnessed a revolution in the scientific landscape, attributed to nanoscience growth, which refers to the area of science that deals with materials having at least one dimension at the nanoscale, mostly under 100 nanometers. Those materials are considered one of the most impressive and applicable fundamentals in today's research, owing to their remarkably small size and significantly large surface-to-volume ratio. Nanomaterials have enhanced properties both physically and chemically compared to their bulk composition. But how exactly small is the nano? In the International System of Units, the prefix nano means 1 billionth. Therefore, 1 nanometer is 1 billionth of a meter. With this huge shrinking in size comes new challenges, one of which is determining the characteristics of these small sensitive materials. The scientific community is aware that there are differences between the way analytical characterization methods operate for nanomaterials, in comparison to the more traditional approaches used for more conventional macroscopic materials. This has led to a revolution in the development of advanced characterization devices, designed to carry out one or multiple characterization techniques, to identify the unique measures that determine the potential and application of these nanomaterials. The most basic parameters measured for nanoparticles are their composition, size and size distribution, along with their surface area, which have a huge influence on their performance and properties. Other important measurements are their surface morphology, surface charge and crystallography, in addition to their concentration and agglomeration rate. One of the most powerful and important characterization techniques in the nano world is the microscope, which is mostly used to determine the size, shape, and morphology of nanomaterials. Electron microscopes have emerged as a powerful tool for the characterization of a wide range of materials. Their versatility and extremely high spatial resolution render them a very valuable tool for many applications. There are two main types of electron microscopes. The first one is the transmission electron microscope, which uses a beam of electrons that transmits through a specimen to visualize it and generate a highly magnified image, since it can magnify objects up to 2 million times. The sample measured by this microscope must be very thin and conductive. An electron gun at the top of the microscope emits electrons, which travel through the microscope's vacuum tube, to the electromagnetic lens, then focuses the electrons into a very fine beam. The beam then passes through the specimen, and the electrons either scatter or hit a fluorescent screen at the bottom of the microscope. An image of the specimen with its assorted parts shown in different shades, according to its density, appears on the screen. The other type of electron microscope is the scanning electron microscope, which produces images of samples by scanning the surface with a focused beam of electrons. And it can magnify objects up to 1 million times. It provides high-resolution images, delivering information about the topography, morphology and crystallography of the sample. In addition to being a useful instrument for evaluating various materials for surface fractures, flaws, contaminants or corrosion. Samples measured must be completely dry, and small enough to fit on the specimen stage. They should also be electrically conductive, and electricity grounded. so they may sometimes need special preparation to increase their electrical conductivity. Furthermore, they should withstand the high vacuum conditions and the high energy beam of electrons. Tissues and soft-bodied organisms require chemical fixation to preserve and stabilize their structure. They are imaged using an environmental mode, or low-voltage mode of scanning electron microscope operation.
The electron gun produces a source of electrons, and accelerates them into a series of condenser lenses, which focuses the electron beam, as it moves from the source down the column. After the beam is focused, scanning coils are used to deflect the beam in the X and Y axes, so that it scans in a raster fashion over the surface of the sample. Detectors above the sample collect electrons scattered. The signals are then displayed on the viewing screen, and the operator will control the brightness and the intensity until a reasonable clear image is obtained. To overcome the drawbacks of the scanning electron microscope, such as its limitation in scanning different types of materials, and to develop a way to provide a quantitative data on a variety of surfaces, atomic force microscope was invented. The atomic force microscope is a type of scanning probe microscope used for mapping the atomic scale topography of surfaces. It uses the forces between the surface and the tip of the probe, moving above the surface, with a resolution of fractions of angstrom. It has the advantage of imaging almost any type of surface, including polymers, ceramics, composites, glass, and biological samples. It can also be used in vacuums, air, and liquids with minimal sample preparation. The atomic force microscope uses a laser beam deflection system, where a laser is reflected from the back of the reflective cantilever that holds the sharp tip onto a position-sensitive detector, which will then be translated into a three-dimensional topographic image, with a variety of data probed. The atomic force microscope is used to image the topography of surfaces, in addition to providing data on the adhesion strength and mechanical properties of materials. It can also measure the electrical forces, conductivity, capacitance, and surface potential of different types of materials. Another powerful characterization technique is spectroscopy, which allows the study of how matter interacts with or emits electromagnetic radiation. There are different types of spectroscopy, depending on the wavelength range that is being measured. For example, the ultraviolet visible near-infrared spectrophotometer studies the absorbance or the transmittance of light in the visible, ultraviolet, infrared regions with a wavelength range from 175 to 3300 through a sample to determine its chemical or physical properties. The absorption of light by a chemical compound will result in an increase in the energy content of the atoms or molecules, leading to the excitation of their electrons from the ground state towards a higher energy state. And each material will have a unique spectrum, with absorbed radiation energy equal to the energy difference between the higher energy state and the ground state, revealing the material type, particle size, concentration, and quality of the sample. Both films and solutions can be characterized using this technique, needing different processing. For example, liquid samples are diluted with an aqueous or non-aqueous solution, depending on their type, and are placed inside a special transparent cuvette that can be plastic, glass or quartz. First, the light source generates a broad band of electromagnetic radiation, which will then travel to the monochromator. In the monochromator, the light will refract into separate beams of wavelengths. One wavelength of light will make it through each time, After the light passes through the sample, it is caught by a photocell detector which converts the light into an electrical signal. Then it is sent to a recording device that stores all the data generated, and produces the spectrum of the desired compound. Using these spectacular techniques, we have seen beyond what the naked eye can see. We have explored new worlds, laying inside each corner of our visible world. And the scientific curiosity is pulling us further to explore what is smaller than the nano. Diving in what is called the femtotechnology,